Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry Made Easy. In this video we're going to be looking at acids and bases, and we're going to be using this to come up with the idea of conjugate acid-base pairs, and then talk about the different types of acids that we can get. So firstly, we've got to talk about the Bronsted-Lowry definition of an acid and a base, and this all centers around the idea of a proton or a H+. Now, acids are known as proton donors, so they release a proton or a H+. And if we call the generic acid A, when this acid is in a aqueous solution, what happens is a proton, at least one proton, dissociates away from the rest of the molecule, and the rest of the molecule is A. So what happens is we have a H+ and the counter ion, the A-. So remember, they were neutral on the left-hand side, so the charges on the right-hand side have to equal the same. Now this, in this case, is called a monobasic acid, as one proton is released. An example of this would be hydrochloric acid, where it dissociates to form H+ and the Cl-. So you can see quite clearly that the Cl is your A, your rest of the molecule. Now, there are other cases of acids that are dibasic. Example is sulfuric acid, and what happens is it has two hydrogens that can dissociate as protons, leaving behind a sulfate ion. And so the rest of the molecule here is the sulfate, which becomes A2-, and remember the charge on the right hand side, there's two lots of H+ and 2-, collectively is neutral, has to match the neutrality of the left hand side. Here, this example, phosphoric acid, releases 3 protons, therefore leaves behind an ion that will be of equal charge, so we've got the PO4 3- ion, and so that our rest of the molecule is always this counter ion, in this case it's the 3-. It is really key that you understand that the actual acid is the HA part, because this is the thing that donates the H+. So anything that releases the H+ is your acid. Bronstedlowry base is one that accepts this proton. When a Bronsted-Lowry base accepts the proton, it then becomes BH+. This base could be neutral and have a lone pair, example being ammonia, and when this picks up the proton, it becomes ammonium+ ion. Again, we can check because the charge over here was positive over the two chemical species, and even though we've got one, the charge should match either side. So we've got H+ here, and you're going to have a H+ here. Sometimes you can have something that is negatively charged. So often you see this with oxygen-containing species. So here we have a carboxylate, the ion version of a carboxylic acid, and when it picks up the H+, it forms the carboxylic acid whole. This time, the actual formed species isn't positively charged, as this generic formula would make you believe, but you can see here that the minus and the plus here equals 0, and the charge on this side is also 0, so we know we've got the correct species. And so that's a really good tip to always check whenever you're dealing with any sort of ionic equations, that the sum of the charges on the left hand side and the right hand sides balance. And you have to add up every species individually on that side of the arrow. Now, given that the acid is a proton donor and the base is a proton acceptor, it's unsurprising that they react together. And you've known this from very early on in your scientific careers. Acids and bases react to form a neutral compound. Not just any old base, it is an alkali. The definition of an alkali is a soluble base. So if you were to take an acid and alkali, you get salt and water, as long as these were equimolar equivalents. And so this is our simplest full symbol equation for a monobasic acid, HCl, reacting with sodium hydroxide, an alkali. In order to get this into an ionic equation, we need to split any acid and alkalis into their corresponding ions. And we also need to split any salts. So what I'm going to do here is I'm going to split the HCl and the sodium hydroxide into their ions. And then because sodium chloride is a salt, I need to split that up. But water I don't need to split because it's neither an acid, a base, or an alkali, or a salt. Then what I need to do is remove any spectator ions. And spectator ions are those whose charges have not changed on the left-hand side of the arrow to the right-hand side of the arrow. You can see the H plus has changed. It's ended up in water and it's neutral here. So we're going to keep that. That is not a spectator ion. Cl minus has not changed. So we're going to discard that. Sodium plus has also not changed. So we're going to discard that. And the hydroxide has changed as it's ended up in the water here. So we're going to keep that. And so that now leaves you with your ionic equation. And no matter what acid and alkali you've got, you're always going to have versions of this ionic equation. They also react with reactive metals. For example, calcium reacts with 2 moles of hydrochloric acid to form calcium chloride and hydrogen. So this follows the MASH acronym, where metal, calcium, acid, hydrochloric acid gives salt. This is our salt here because we've got a metal and a non-metal, and hydrogen. This is a full symbol equation, and just like before, to get an ionic equation, you would split each of these into their individual ions. Calcium is obviously neutral because it's a metal, but calcium here in a salt is calcium 2+. And then you'd remove any spectator ions. And so our spectator ions here, H plus has changed, so we're going to keep that one. Calcium has changed, so we're going to keep that one, but the chlorides have not changed, so we're going to discard them. So you end up with this as an ionic equation. Also react with carbonates, so any metal carbonates, to form a salt, water, and carbon dioxide. And again, by going through the same step we did down here, split any acids, bases, or salts. Get this long equation here, where magnesium carbonate is split up. Two HCl's, that 2 is showing we've got 2 lots of protons, 2 chlorides, and then what we need to do is remove any spectator ions. And these are any that have no change in charge going from this side of the arrow to this side. So you can quite clearly see magnesium and chloride are the same on either side, so we're going to get rid of them because they're spectator ions. And that leaves us our ionic equation for the carbonate reacting with a acid. This would be the ionic equation for any acid reacting with any metal carbonate. It always boils down to this. And so you can see how this process is helping us each and every time. Now the other thing acids react with that you need to be aware of is with metal oxides. Here is an example of 2 moles of hydrochloric acid reacting with magnesium oxide. It forms salt and water. So very similar, as you can see, as an acid reacting with an alkali. And that's because metal oxides are just bases. So they follow the same pattern of bringing the products of salt and water together. Now the ionic equation is going to be splitting up the salts, checking the changes, and you'll end up with this as your ionic equation, following exactly the same process we've done before. And so you need to know all these different types of reactions of acids and be able to come up with their ionic equations if asked. Okay, so before we look at conjugate acid and base pairs, what I want you to do is do these questions here. So just quickly, 1 to 3 is to just draw the ionized products when you add each of these acids to an aqueous solution. And then questions 4, 5, and 6, what I'd like you to do is for part A is to complete the symbol equation and the products for each of these reactions of acids. And your acids here are these acids here. And then for part B, I want you to construct the ionic equation that shows only the ions that change charge and the species that change charge in the reaction. So no spectator ions for B. Pause the video here and have a go. Okay, so for questions 1, 2 and 3, the rest of the molecule here is underlined in grey. And so your products are going to be, and you can see here that as we've talked about before, because of the charges cancelling each other out on the right hand side of the equation, they're equal to the neutral left hand side of the equation. For questions 4, 5 and 6, I'm going to just do first the A parts. So here we have a metal carbonate reacting with an acid. So we're going to form calcium sulfate as our salt. That's obviously aqueous because it dissolves in the water. Carbon dioxide as a gas, and then water as our liquid. For 5A, we've got a metal oxide reacting with this acid here. Now calcium is 2+, so it needs 2 bromides, Br minuses, to counteract that, and hence we needed to put 2 in front of here, and then water. So you always get salt and water for that. And then 6A, this is an alkali with an acid, so you get salt and water form. Okay, the ionic equations, the ions for 4A, and then we need to remove any spectator ions, so any that don't change. We've got our sulfate there, got our calcium, that remains to give us carbonate 2- plus the 2H plus goes to carbon dioxide and water. You should include state symbols here as well, and they'll be exactly the same as what's in the symbol equation above. Here's the ions for 5A. So we've got calcium doesn't change, neither does the bromide, so we're cancelling them out. Here for 6B, we've got our Na plus is exactly the same either side, sulfate is exactly the same, so we end up with the equation as so for an ionic equation. Now you can see we need 2 H pluses because we have a dibasic acid that we are using. Okay, now if you're just looking at this in year 1, you can stop here and that's all you need to know. If you're looking at this with the intention of doing the year 2 topic on pH calculations, then we're going to look at the next concept, which is conjugate acid and base pairs. So next we turn our attention to conjugate acid and base pairs. And they all are based on the Bronsted-Lowry definition of both an acid and a base. Now if we turn our attention to this equation here where we've got hydrogen chloride gas dissolving in water, so we're adding water to it. This forms 2 species. First of all, the chloride anion, and then also this species here, which is known as the hydronium or hydroxonium ion. It's basically water with an extra hydrogen on it. Here we have water. If you then add the H+, you get this, the hydroxonium ion. Most important is that we look at the roles of both the forward direction, so these being the reactants going to the products, and the backward direction where these are the reactants and these are the products. Now here HCl in the forward direction is acting as an acid. You can see this hydrogen has dissociated away from this acid to form Cl-. To look at the equation that we've looked at before, this is kind of what we're substituting in here. This is our HA, this is our A-, and our H+ has become an adduct with the water here. So if this is acting as an acid, that must mean that the water is acting as a base. So this is going to be an acid-base reaction. And so you can see the water is acting as a base, picking up the H+, which has come from the HCl, forming this hydroxonium ion. And so the overall change is as followed here generically. Our acid releases H+, that H+ ends up being joined onto the base, and we got our A-. So that was from the point of view of the forward direction. Now if we were to then take these as our reactants and make these the products, so looking at the backward reaction, then you can see that this time the hydroxonium ion is actually acting as an acid, because when it goes to the water, which is the related species, then it has lost one of these hydrogens as a H+. And what has actually happened in this direction, the backward direction, is the chloride has acted as a base, as it's this chloride that accepts the hydrogen from the hydroxonium ion to form HCl. So we say that there are conjugate acid-base pairs. So for example, take this HCl. The related species to this is chloride. In the forward direction, the HCl acts as an acid. And then on the backward direction, the chloride, the resulting chloride, becomes a base. This is called a conjugate acid-base pair. You could label this as A1, A for acid, 1 because it's the same species, and this one as B1, B because it's a base, and the 1 is showing that these two are linked together. In this case here, there's a conjugate acid-base pair between the water and the hydroxonium ion. This is going to be called A2 because this is the acid in this case, and the 2 to designate it is different from this pair. And then the water is going to be B2 as this is the base for this acid. An easy way to identify a conjugate acid-base pair is you'll be looking for species that differ only by a hydrogen in the forward and backwards direction. So if you look here to here, these are both a pair and they differ only by a hydrogen. As with this water to the hydroxonium ion, there's only a difference of 1 hydrogen in there, so we know that they're the pairs. And then you just got to think from their point of view, are they losing or are they accepting a H+? So what I'd like you to do now is pause the video and have a go at these equations here and see if you can come up with the 2 conjugate acid and base pairs for each of these examples. Pause the video here and have a go. Okay, so for the first one, know that these 2 species are related. There's a difference of only a hydrogen in each, so they must be a pair. This one is the one losing a hydrogen as it goes forward, so we know that this must be an acid. Just to clarify, as this goes into this direction from right to left, it is picking up or accepting a hydrogen, so this is our base B1 to show that they're a pair. This water here, as it goes into this direction, what has happened, think of the change, it's picked up a hydrogen. So in this case, it's acting as a base. B2 to show that it's a different pair, B for base. And then just to clarify and make sure we've got the right idea, if we track this turning into this, then what we can see is it's losing a hydrogen. So it's donating a hydrogen, so it must be acting as an acid, so this will make it A2. And this makes sense, you're always going to have an acid base on one side and an acid base on the other side of your arrow. There's a strange example here because you've got a weak acid with a strong acid, so it's no surprise that the strong acid is more acidic, so it will act as the acid. To this chloride because there's a hydrogen difference, and as we can see here, we're losing a hydrogen to form this species, so it's acting as an acid, so we're just going to call this A1. And on the way back, the chloride is picking up a hydrogen from this species to form HCl, so it's acting as a base, so we're going to call that B1. Worked out one pair, the other pair should be the opposite, so if you're taking acid, this must be a base. And we can test that it's a base because as we go from here to here, it needs to have accepted a hydrogen, and it has. We've got 2 here versus 1. And then on the backwards direction, going from right to left, it has lost a hydrogen. So this means it's an Bronsted-Lowry acid. So we're going to label that A2. A strange example where you've got 2 acids together, sulfuric acid with nitric acid, where one is always going to be stronger than the other. So one will always act as the acid, whilst the inferior acid will act as the base. See that these 2 are obviously related by 1 hydrogen. As we go from this direction to this direction here, then what has happened is we've lost a hydrogen. So that must mean this is an acid. It's lost a hydrogen. And on the way back, this has gained a hydrogen. So this is our base. And therefore, this must be B2 going to A2. Okay, so just a couple of exam questions to test this and put it into practice and see how it looks. Pause the video here and have a go at this one. Okay, going through the answer here, you've been told first of all that 2-hydroxypropanoic acid is a stronger acid than butanoic acid. It means just 4 carbons. So this one here, 1, 2, 3, 4 carbons is your butanoic acid. That is going to be weaker than this, which is our 2-hydroxypropanoic acid. Based on that, our stronger acid is going to be the one that donates a H+. The butanoic acid, being weaker, is going to be the one acting as a base. What I've drawn here is the species that arises when this hydrogen here, which is part of the carboxylic acid group, the acidic group, actually dissociates away from our acid. Think of this as our HA, and A is everything here across to the left of this line. So this is our A-. H+ has been picked up by this base here. So this butanoic acid is going to pick up that H+. And when it picks up that H+, it becomes positively charged. You can see here we've gone from 1 hydrogen to 2 hydrogens. But it makes sense because if we've got a negative charge here, we need a positive charge here to make this side of the equation, arrow, neutral. Because a minus and a positive is 0. Because this side of our equation is 0. We've got 2 neutral species. Remember to always check your charges either side of your reaction arrow. And it's asking you to identify the conjugate acid-base pairs. Remember, you're looking for any pair is anything with just a difference of a hydrogen. So straight away, say that this is a pair. You can see that that is a pair. Remembering that this, as it turns into the other side of the equation, has lost a hydrogen. So it must be this species that in this pair is the conjugate acid. Therefore means this must be the base, and we can see that because this picks up a hydrogen when we go from right to left, acting as a base by accepting a hydrogen. And then this one here, by virtue of it being next to an acid, it must be a base. Label that B2 to show 2 to show that it's a second pair. And then this one here, therefore if this is B2, this must be A2, acting as an acid. And we can just check this. Is this, when it goes from here to here, picking up or accepting a hydrogen, like the Bronsted-Lowry definition? Well, it is. It's gone from 1 hydrogen to 2 hydrogens. And then on the reverse, is this losing a hydrogen, like an acid would donate a hydrogen? Yes. Okay, the final exam question I want you to apply this knowledge to is this question here. Now, if you haven't come across Ka yet, I'm just going to give you a little hint that allows you to answer this question. That is just that the larger a Ka value is here, and you've given 2 values for the different species, reactant species, then the stronger the acid. So that will help you decide which one's going to act as an acid or a base in this pairing. Pause the video here and have a go. Okay, so first of all, you know that this is the ethanoic acid, and because this value is smaller, this one is not as strong as this acid here, fluoroethanoic acid. So this is your stronger acid, bigger Ka value. In mind, the weak acid will act as a base, and the strong acid will therefore act as an acid. And so the fluoroethanoic acid is going to be a H+ donor. Just drawn out the first bit of this. The carboxylic acid bit is always the bit that loses the H+. So that is the version when this H+ here has been lost because it's been donated. And so with this donated, it must move on to this molecule here, the ethanoic acid, which is going to act as a base. So we're going to draw this with an extra hydrogen on. You pick up an extra hydrogen, it's going to be positive, and we can always check because this side, they're both neutral. So our right-hand side of the equation always needs to be neutral, the sum of it. We've got a plus here and a minus, so they cancel each other out. So we know it looks good. And then it's asked you to label the conjugate acid-base pairs. Know from our working out here that this ethanoic acid must be a base. So we're going to label that as B1. And these basically refer to where they are. And its conjugate pair is going to have a difference of just a hydrogen. So the conjugate pair must be this one here, has an extra hydrogen. And so this must be number 1 as well. And if this is a base, this one must be an acid. So we're going to put an A here. So those two are a pair. Now we can just check, because if we went from here back to its pair, it has donated a H+, and it has. And then, as we said, this fluoroethanoic acid is going to be an acid, so we're going to have to label that A. This is a different pair, so it's number 2. Its pairing is this one here. There's a difference of a hydrogen, so this is also 2. And because this is an acid, this must mean that this species here acts as a base, and we can always test that out. Because as we go from here to here, are we donating a hydrogen? Well, we are, because this is becoming, it's lost a hydrogen. And going from here to here, are we picking up a hydrogen? Well, yes, we are, because this has got hydrogen in. So in this video, we've covered quite a lot of different things. We've looked at the definition of an acid in terms of Bronsted-Lowry, and we've also looked at the definition of a base. We've come across conjugate acid-base pairs. We've looked at monobasic, dibasic, and tribasic, and then we've even looked at ionic equations, etc. So if this video has been useful, ensure that you like it, and then ensure that you subscribe to the YouTube channel for new videos as and when they're uploaded.